Hi everybody. Today I'm going to surprise or maybe disappoint some of my YouTube subscribers, but I'm going to make a video that's not about my log house. I have other interests, and today I'm going to make a video trying to help you imagine 4 dimensions. So I'm going to have you exercise your imagination to visualize what a 4-dimensional object is like, even though there are no such objects available to us. Your imagination is pretty strong and powerful, so you're going to be able to do it, so don't worry about it. Part of what you already do is imagine other dimensions. For example, you imagine 2-dimensional figures, even though there aren't any such things. All of our 2-dimensional figures are really 3-dimensional. The ink has a certain depth on a picture. You can imagine 1-dimensional things. You can imagine lines, even though there are no such lines available to us. Even if you had the tiniest spider web, or even, say, a string of DNA that you could stretch out, there would be such a tiny line. It's still not 1-dimensional because it does have a 3-dimensional structure. The chemists would tell you that the atoms that make it up have a certain size, even though you can't see them. They're too small. So we can't see 0-dimensional points or 1-dimensional lines or 2-dimensional surfaces, even though we think we can see approximations of them. We see 3D objects. And actually, we don't even see 3D objects. We see 2-dimensional manifolds, that is, the skins or the surfaces of 3-dimensional objects. So it gets a little tricky when you get down to the fine points. We won't get down to the fine points. We'll just imagine. We can imagine a point. I can tell you, imagine a point. It has 0 size. It's just one little dot. And I can say, imagine that the end of this little piece of copper wire is 1 point. And you can imagine that. And so for a 1-dimensional line, we can imagine that this little piece of copper wire is a segment of a line. And that's fair. It's not cheating, even though this wire might be 14 or 12 gauge. We can imagine that it has no width or depth. It's just length. So that's the kind of imagination we're going to do. It'll be a little bit coarse when you think about the fine points, but we won't worry about that. Now our strategy, since we already can imagine 0-dimensional things and 1-dimensional things and 2-dimensional things and 3-dimensional things, we will just carry that momentum over and imagine 4-dimensional things and even 5-dimensional things. We won't dwell much on 5, but we'll do it. So the objects we're going to imagine, let me show you some examples. Here's a 3D object. One thing I want to point out is that this is a 3D object that I am manipulating, but you have to imagine it because you can't see 3D. If you were here, I could hand it to you, but since you're looking at it through the video, you're seeing a 2D projection of this 3D object on your screen, and since it's a fairly familiar object, you see, oh yeah, I see that's a 3D thing. And when I rotate it, that helps, because even though you don't have binocular vision on your screen, because I only have one camera, you can see the effects of parallax on this object just because I'm moving it and rotating it. So it helps to rotate to see 3D. Now, for objects, the simplest object that we could discuss probably is the sphere, 3D sphere, and then talk about a 4D hypersphere. And we could talk about the progression going from a circle to a sphere, and from a line segment. Believe it or not, this is a 1-dimensional sphere, just a line segment with 2 endpoints. And then a 0-dimensional sphere is just a point. A point is the only figure in 0 dimensions, and that's what all figures are in 0 dimensions, are just one single point. So we could talk about that, but it's hard to visualize spheres. They all look like circles, so we won't do hyperspheres. Now the next most simple, or the next simplest figure would probably be triangles. So you take a one-dimensional line segment, you go up one dimension to 2 dimensions, and you get a triangle. And then moving up to 3 dimensions, the triangle generalizes into a pyramid or tetrahedron. And we could generalize and go to 4-dimensional pyramids, but we will not do that. Instead, what we're going to do is we're going to generalize a square. And so we're going to progress from a 0-dimensional point, like the end of that wire, to a 1-dimensional line segment. We'll call this line segment an edge, because it'll remain an edge even in higher dimensions. We move up from an edge to a square, and again we'll use the term square for these because as we move up in dimensions it will remain a square. Now we have to stop here and talk about really what this square is. Do we mean just the boundary that's made out of copper in this case, or do we mean the entire surface so that we could paint it? And really a square is the surface, and we're going to cut that corner and say, wait a minute, we're not going to fill in the inside of the square because it makes it hard to see. You can't see behind that. So we're going to, in our model making, we're going to stick with just the edges. And when we make a cube out of 6 squares, as you're familiar with, we will not fill in the squares. We'll leave just the edges. And so we'll have this kind of a figure so that you can see through it and you can see the back side of it. That's not the way we see cubes in real life, but for this demonstration it's going to help us be able to see through the thing. So we move up 1 dimension from our normal 3-dimensional cube, and we get our 4-dimensional hypercube. And this is what we're going to concentrate on. This is a 4-dimensional, it's actually not a hypercube, it is a 3-dimensional projection of a 4-dimensional hypercube. And not even that. It's a 3-dimensional projection of the edges of a 4-dimensional hypercube. Because as I said, all we have here in copper is the edges of the various squares and cubes. And if we filled in all the squares, and then in 4D you'd have to fill in the solid middles of all the cubes, you just have a blob that wouldn't show you much detail. Now, this method of progressing can be extended. I've extended it to 5 dimensions. So here's a 5-dimensional hypercube, and we won't do anything more with this because it is very difficult to visualize, and we're going to have our hands full visualizing 4 dimensions. But just be aware that you can build 5-dimensional models. Here's a 3-dimensional model of the projection of the edges of a 5-dimensional hypercube. And from this you could count how many corners and lines, edges, and so on are in the thing. Now, I want you to think about 3 different entities to which dimensions apply. One is the object. So if we have an object, we could say we have a 3-dimensional object, or we have a 1-dimensional object. So that's what we're talking about, is objects with their dimensionality. But another thing we could talk about is projections. So, for example, here's a 3-dimensional object, but if we cast a shadow of it on a white surface, we would have a 2-dimensional projection of a 3-dimensional object. And that's what's going on here, as I mentioned. Here we have not a 4-dimensional object, but a 3-dimensional projection of a 4-dimensional object. So you have to keep those terms straight. projection and object because they will have different dimensionality. Almost all of the figures that we deal with are two-dimensional projections of two- or three-dimensional objects. Now there's a third entity, and that's the observer, and that's you and me. Now I am a 3D guy in a 3D room, and what I have to manipulate here are 3D objects. You are a 3D person, and you're not in my room. You're looking at a 2D projection of my 3D environment and of my 3D objects. But yet, you as an observer can imagine the dimensionality of the objects and the projections that you're seeing. So you want to kind of keep those straight. When we get up into 4 dimensions, you have to imagine that you are a 4-dimensional observer, not a 3-dimensional observer. And you kind of have to bring along or imagine that you have some extra insight that comes with being a 4-dimensional person so that you can imagine the things we're going to be talking about. Now, there are some words that describe parts of figures in different dimensionalities. Let me just go through them from 0 dimensions to 3 dimension. And the most general, in 0 dimension, you can only have points. In 1 dimension, you can have curves. Think of those as mathematical curves. They're bent lines is what they are. In 2 dimensions, you have surfaces. Those again are curved. Those are the things you can paint. And in 3 dimension, we have space. That's because our space is 3-dimensional, so we call it space usually. But to be more specific, rather than those general terms, in 0 dimensions, we're going to talk about ends. Actually, the most common term is end point. So when we have, say, for example, a 1-dimensional line, the thing that characterizes or distinguishes the line are the end points. And so if we specify 2 points on the line, we've determined a line segment. In a 2-dimensional figure, like a triangle, it's common to call them vertices or a vertex. These are the points, the 3 points that make up the corners. But I prefer, what I'll use is the term corner. Because corner, even though it doesn't seem like the end of this line is a corner, in all the rest of the figures, when we go to 2-dimensional, we consider that to be a corner. And in 3 dimensions, we talk about the corner of the room where 2 walls and a floor come together. So corner works for that. And I'll use that term corner to talk about the vertices on a 4-dimensional hypercube. So similarly, even though in 2 dimension these I said are surfaces, but if they're flat they're called planes. But in our case, since we're going to look at this particular figure, we're going to call them squares. Think of those as 2-dimensional figures. And in their job in a square, they're called or in a cube, they're called faces. We may use that word faces from time to time. Now, when we get into the components of a hypercube, we have these figures which we are going to call cubes. They're 3-dimensional figures that appear not only in 3 dimensions, but they appear in the 4-dimensional structure as well, and also in the 5-dimensional structure. Now, we're going to imagine constructing a hypercube. And that's we're going to put our mind to work imagining how we would build a hypercube. Not how we would build a model of a 3-dimensional projection of the hypercube in copper wire like I did. I'm not going to tell you how to build this, although that's fun and I might do that in another video. But I want you to imagine what it would be like if you were a 4-dimensional person. You had a 4-dimensional gift you wanted to give someone, and you needed to make a four-dimensional box to put that gift in. That is, you're going to make a box that's got squares as its components, just like if you were a two-dimensional person, you had a gift, this would be the box you'd put it in, just a square, because the gift would be inside and it would be contained by the sides of this box, and you could hand that to the two-dimensional recipient. If you're a three-dimensional person like you and I are, and you have a gift, you have to have a box, something like this. And you put the gift in the box and it's all enclosed, it can't get out. Now you can hand it to FedEx. If you're a four-dimensional person, you have to have a four-dimensional box that encloses a chunk of four-dimensional space. You can put your gift inside and it can't get out because it's got boundaries around it. Now the boundaries are cubes. Just like the boundaries of this box are squares. And just like the boundaries of this box are line segments. And just like the boundaries of a line segment are those two endpoints. So in each case, the boundary is one dimension less than the figure. And so in this case, the boundary in 5 dimensions would be hypercubes would be the boundaries. That is, four-dimensional hypercubes. Incidentally, there's a word you might have heard of, tesseract. And I don't really know what the word means. I think it means a two-dimensional projection of a three-dimensional edge model of a four-dimensional hypercube. That is, if you look at the shadow of this thing, I think that figure on 2 dimensions is called a tesseract. But it may be that tesseract is the term for a four-dimensional hypercube. I'm not sure exactly, so I won't use the word. Now, what we're going to do, as I said, is we're going to imagine building a four-dimensional box that we can put a four-dimensional gift in. And we're going to do it 2 different ways. One is by dragging, and the other is by folding. So first I want to just show you the dragging procedure because it's the simplest and it's the easiest to get your mind around exactly how you would build a hypercube. In fact, that's the way I built these copper ones. So for dragging, we're going to do this in increasing dimensions, and we're going to do that deliberately because I want you to imagine the process you go through from one step to the next, to the next, to the next, to the next, so that when you go into the four-dimensional process, it's just natural. That's just what you've been doing all along. So at 0 dimensions, we only have a point. That's all you can have in 0 dimensions is 1 point, and we have one right there. Now, to construct a line segment, which is the one-dimensional equivalent of a square or a cube or a hypercube, you take that 1 point and you drag it for some distance. And imagine it was coated with ink and it just leaves a track. Or you can imagine just taking that point and taking a second one some distance away and then filling in between. And so what you get is a line segment, like this. Okay, that's easy enough. And all it took to construct this was to start with 1 point and drag it through space in some direction. Now this is a direction you didn't have before. The direction horizontal here in this picture is a dimension that did not exist in the 0-dimensional case. So we're dragging it in a new direction in the new dimension. And that new dimension in this case is horizontal, and we get this line segment. Alright, now the next step is you're going to take that line segment and drag it in a new direction that's perpendicular to all the other directions you have. The only other direction we have is horizontal, so perpendicular to that, we could do it vertically down the page. And so we take this line segment, drag it down the page for the same distance of its length, and we get this square. Now, here again, I have to remind you that when we drag this across, we're really filling in the whole square. But just for visibility, what we're going to do is say we are going to just leave the edges and not the middle. So instead of dragging, again in this case, you could think of just taking your initial edge, establishing a second one some distance away, that is this distance away, and then drawing the lines across between the endpoints. So you can think of it as taking two of the things you had up here and connecting the endpoints, or the corners. We're going to call these things corners. So you take two of these figures, separate them by this constant distance, and then connect the corners. So then we move on to 3 dimensions. You take the square, let's say it's this one right here in the front, you take a second one, that's the one behind it, and now we've got to go in a third direction, which I don't have on this paper. I've used up my horizontal and my vertical, so the new direction has to be perpendicular to the paper, which I have here in my 3D room. You don't have on your screen, and I don't have on this paper, so I can't draw it, but I can. Now we can use our imagination to imagine that these diagonal lines are really perpendicular to the paper, and that they go into the paper or out of the paper. And that's a real common thing for us to imagine, so there's no problem. And if you're adept at drawing, you realize that to see this cube this way, these are really not squares. The angles are distorted. You have a pair of obtuse and acute angles, and you may be able to see that in this. Let me just have you look at a few different projections of this. If I aim it right at you, then you see squares. In fact, you would see one square inside of another with the angle, with the corners connected, making 2 squares and 4 trapezoids. But as I turn it, you get a more familiar Necker cube, it's called, a picture of the edges of the cube. And if I put a diagonal of this cube aimed directly at you, like this, if I can do that, you'll see a hexagon. It would be a regular hexagon with all of the radii going to each corner. And that doesn't look like a cube. It looks like a flat hexagon wheel. And so typically to draw a Necker cube or to draw a projection, you put the diagonal, you have it off a little bit so that the diagonals don't line up. In fact, so that no lines line up. And that gives you the best looking projection that we're used to for imagining the cube. And we'll use that same trick when we go up to the Hypercube. Now, I don't expect you to get much out of this picture. It gets complicated very fast. But the way you make this picture is you take 2 of these, that is 2 Necker cubes, and you draw them on the same page with separated by that same distance, and then you connect all of the corners. Connect this corner to its corresponding to the new cube, this one to its corresponding corner, this one, this one, this one, this one, this one, and this one. You connect them all together. And so what I did to make the Hypercube is I made 2 cubes that were not square. That is, I distorted them so they're made out of parallelograms instead of squares. But I made 2 the same, and then had them close together, this same distance as one of these wires, and then just soldered a wire between each corresponding corner, and you get this. And then you take 2 of these and do the same trick, and you get 5 dimensions. So that method of construction is the simplest way to think about it, and it's the easiest way to actually build a model. But it doesn't give us the feeling about how would we wrap a 4-dimensional gift in a 4-dimensional box. And for that we need to use the second method. Other than dragging, we'll use the folding method. So that method, it actually makes a box, and it's the way we would make a box if we had a three-dimensional gift to wrap. And in the 3D case, we would start with a pattern like this. Very familiar pattern of 6 squares, and then we would fold them up. These 4 that are touching the middle one become the sides, and this last one that's hanging out over the edge flips over and becomes the lid. So that's a familiar process to us. So let's back up to generalize that process and then follow it through to 4 dimensions. You can probably already see ahead. Let's start with a one-dimensional line segment as our starting figure, and then see how we would make a box for a two-dimensional gift. So we start with one-dimensional line segment, and the rule is this. You put that one segment down someplace, and I put it right here. You take another one and stick it on each of the boundaries. So the line segment has 2 boundaries. It has 2 endpoints, this one and this one. So you take another one of these segments, put it on this boundary, hook it onto the boundary, and another one hooked onto this boundary, and when you're done with that, you take one last one and hook it onto the end, either end. Now those boundary points, the boundaries, become hinge pins. You're going to fold on the boundary. So you can see in this picture right here, we take this point and consider it to be a hinge pin and just fold that line segment straight down 90 degrees, and it'll come down into this position. Then we take these 2 and fold them down, and they go into this position. And then finally we take this boundary here and fold the last one up into place, and we get a square. And we can imagine our two-dimensional gift going in here. We close the lid, tape it up, and send it off to two-dimensional FedEx. Now, moving on to 3 dimensions, we take this figure that we have just built, we plop it down, and let's say this is the one we plop down, and on each boundary we stick another one. So now the boundaries of the square are line segments, they're edges, they're not corners like this. And they're still going to serve as hinge pins. And that's fine because our hinges we have in 3D are line segments like that, so we have no problem with that. So we plop this down in the middle, we plop another one on each boundary, so the boundaries coincide. And when we're done with that, we plop in one last one, and it can go anywhere. It can go here, or here, or here, or here. And then what we do is we consider those boundaries that are common now, common to 2 different squares, as hinge pins, and we fold into the new dimension. Now, you see, if you were a 2-dimensional guy, you couldn't do this because you have to fold these up into 3 dimensions. But we're 3-dimensional people, we do that all the time. And you can easily imagine these sides folding up, making a box, and then the lid folding over the top and gluing on. And you can look at this and see what gets hooked together. This edge and this edge get glued together because these 2 sides come up and those edges meet. Same way with this edge and this edge. Now when you get the box all folded together, you'll see that this edge will be glued to this edge. And this edge will be glued to this edge. And this edge will be glued to this edge. So every edge is glued to another edge, and you end up with a closed box that will hold your 3-dimensional gift. So now that we have that method, let's just move down into 4 dimensions. To start with, we take one of these figures that we just built, one of these boxes. It's a 3-dimensional box or a cube, and we just plop it down. Now it's plopped down in the middle here and you can't see it, but you know it's there. This is an example where it's easier for you to visualize the projection where I filled in the squares, which I did. versus if I left the lines all showing, that's what you'd see, which is a little more complicated. But either way, I think it's easy for you to understand what's going on. We have a cube in the middle, and then on each boundary, and the boundaries in this case are squares, so we got 6 boundaries. We need 6 cubes, and we stick them on those boundaries. There's 1, 2, 3, 4, and then 5, and then the one behind is 6. And when we're all done, we take one last cube and stick it on the end of any place. Now, this might help you visualize that, or it might not, I don't know. This kind of a figure appeared in a Salvador Dali painting when he was trying to depict 4 dimensions, and this is exactly what he was trying to do. To show you how you would build a pattern that you would saw out of 3-dimensional stuff and then fold it up into a 4-dimensional box. It's just like when we want to make a 3-dimensional box, we start with 2-dimensional stuff. We start with cardboard or paper, and we cut this pattern out, fold it up, and we get the extra dimension. We get a 3-dimensional structure that we can put a gift in. The same way with a 4-dimensional person, you'd have to start with 3-dimensional stuff. So this might be wood or whatever. You cut out this pattern, and we could do that in our 3 dimensions. I have a pattern right here. Could make something like this out of wood. But the folding is tricky. For folding, we have to fold these squares together so that this face glues to this face, and this face glues to this face, and this one glues to this one, and fold them up without distorting the cubes. Now, we can distort the cubes and turn them into parallelograms and get a model, and that's exactly what this is. And if you study this hypercube, you can actually imagine, okay, let's say this was the center cube, and then here's the one that folds over this way, here's the one that folds over this way, and you get the 4 of them that fold over, or the 6 of them, and then here's the top. That takes a little bit of study, a little bit of imagination. Here's a model of a hypercube that I made out of wood dowels, and it's painted in various colors, but they all have meaning. Here's the meaning. Each edge, which is all I have built in my model, it's a model of edges just like these are. Each edge participates or belongs to 3 different cubes. So I've painted each edge with 3 different colors. So this edge right here, I have dark blue, red, and yellow. Dark blue, red, and yellow. Dark blue, red, and yellow. So this edge participates in a dark blue cube, a red cube, and a yellow cube. So the red cube is identified by all of the dowels that have red paint on them. So if you look at that, you can see that includes this square on top. They all have red paint on them. This square all has red paint, this square, and then inside here. So I'll hold this by the major diagonal of the red cube. And that uniquely identifies one cube, is by holding diagonal corners. So that's the red cube that this edge participates in. It also participates in the yellow cube, which, if you can see it from there, the yellow cube goes all the way down to here. It's a big cube that's almost cubic. I mean, those angles on that cube are nearly right angles, so it looks like a real cube between my hands, or between these diagonals. And then the dark blue cube, where does it go? There's dark blue on this one. That's the one towards you, this cube right here, these lines. I'll hold the major diagonal on that one also, so you can see the dark blue cube. Now, if you want to really imagine this, you probably have to pause the video and study this thing. Okay, now since I can't hand you this model, which I'd like to be able to do, and let you manipulate it and study it, what I'm going to do is just give you the best picture of it I can and slowly rotate it, and then you can pause your video at various points and then try to think through some of the things we've talked about, look at the colors, and try to make sense of this model. Try to look for the way it was generated by dragging one of the cubes over to its opposite, and you can do that in any of 8 ways, or try to think of it as folding up the pattern to make a 4-dimensional box. So however you want to study it is fine. I'll just give you the best images of it that I can to allow you to study it. And so, as always, thanks for watching. And if you want to see about my log house building or anything else about me, check out the website paulandellen.com. And if you want to see more of these videos, look at the Q Dogs Man YouTube channel.